Welcome students. We are into our seventh lecture of this subject, machine design. We are dealing with unit 1. The subject code of this particular subject is ME303 and the topic which we are going to discuss today is the stress concentration. Myself, Sri Krishna Mishra, assistant professor in the Department of Mechanical Engineering at Suresh Gyan Vihar University, Jaipur. Now, first of all, let's have a look on the lecture objectives of today's lecture. The objectives of today's lecture are first, to understand the concept of stress concentration. Second, to study about the causes of stress concentration. And the third objective is to understand the importance of stress concentration. Finally, we will develop a learning about different stress razors. Means basically we are going to study about the stress concentration, basically what is stress concentration. Then after we are going to know what are the causes of stress concentration, and if there is a parameter to calculate the value of stress concentration, then what is that parameter, what is that factor called, we will know about that. And then after, if there are some solutions to reduce the stress concentration, then what are those solutions, we will have a look on that. All right, so moving into the lecture now. Stress concentration, we all know that till now in the design of machine element subject, the three fundamental equations that were used were like this. First was, as you can see, first was what? First was, as you can see, that load divided by area used to give you the value of stress. This is the theoretical stress value which you were just calculating till now. Then after, there was one bending equation which you used in case there is bending involved in the member. And if there is some torsional stresses which are developed in the material, then in that case you were using the torsional equation. Now these all equations are known as the elementary equations. The all equations are known as the elementary equations. And these all equations, whenever these equations you would have learned, you would have read, you would have known, then at that time you would have seen that there are some assumptions taken while using these equations. And what are those assumptions? The one of the assumption is that there is no discontinuity in the cross section of the component. One of the important assumptions that has been taken while deriving these three equations was what? It was that there is no discontinuity in the cross section of the component. All right, but you all know that in practice, discontinuities and abrupt changes in cross section are unavoidable. You can't avoid the discontinuities. For example, if you have anything you see around yourself, if you have see any product around yourself, if it has some discontinuity, then these equations, you can't use these equations. Why? Because if there are because these equations have been derived by the assumptions taken that there is no discontinuity in the cross section. But if you view around yourself, you will see number of products which have discontinuity. Every product has got some discontinuity. All right, so these three equations therefore can't be used directly. So what is the solution? Now if these three equations which were used, if these can't be used, then what is the solution? If there is some change in the cross section, if there is any abrupt change in the cross section, then what to do? That is important. One more reason is that if we go into the technical aspect, we will see that discontinuities and abrupt changes in cross sections are unavoidable due to certain features of the component. What are those features? Such as oil holes and grooves and keyways and splines, screw threads and shoulders. Therefore, it can't be assumed that the cross sections of machine component is uniform. Under these circumstances, the elementary equations do not give the correct results. Coming into the next slide. Now, as you can see in this diagram, A plate with a small circular hole subjected to tensile stress is shown in this diagram. The distribution of stresses near the hole can be observed by using the photoelastic technique. In this method, an identical model of plate is made of epoxy resin. The model is placed in a circular polar scope and loaded at edges. Now it is observed that there is some sudden rise in the magnitude of stresses in the vicinity of the hole. Vicinity means in the near area, the area which is near to the hole, we see that there is sudden rise in the magnitude of the stress which is developed when the whole of the plate is loaded at some point. Now the localized stresses in the neighborhood of the hole are far greater than the stresses obtained by elementary equations. Now, if you use the elementary equations, then the stress which is obtained by using the elementary equations, that particular value of stress is very much less as compared to the stress which has been found in the area that is near to this hole. In the area there which is near to this hole. Now here is the diagram also which is showing this phenomena. You can see generally these are the stress lines which are showing that stress is uniform at all portion at this particular area. Means the area except in the vicinity of this hole, all the other areas have the normal stress concentration value, stress value. But here in the nearby area of this hole, you see that there is high amount of stress concentration. There is large stress near this hole. This diagram, these are known as the stress lines which are showing the stress value at that particular portion. And as you can see, the stress lines here are very large. This shows that the stress developed here due to the load applied is very large. So basically this particular technique is known as the photoelastic technique. This particular technique of finding the distribution of stress near the hole is known as the photoelastic technique. And this technique has given us the value that there is sudden rise in the magnitude of stress in the vicinity of the hole. Now this localized stresses in the neighborhood of the hole are far greater than the stresses obtained by elementary equations, as I have already told to you. Now moving further, now going into the definition of stress concentration. What is stress concentration? According to the definition, we can define stress concentration, which is also sometimes often known as stress razors. It is also sometimes known as stress razors or stress risers. It is a location in an object where stress is concentrated. What is basically stress razors? It is the location in the object where stress is concentrated. Now where the stress is concentrated? As you have seen in the previous slide, a plate was there and a hole was made in that plate. Now the area near to that hole has high stress value. So that particular location near the hole is known as the area of stress concentration. Why? Because there the stress was concentrated. An object is strongest when force is evenly distributed over its area. Object is considered strong when the force that is applied on it is evenly distributed over its area. So a reduction in area, example caused by a crack, results in a localized increase in stress. So if there is a crack also, that also creates a reduction in the area, and due to that it results in the localization increase in the stress. Stress razors in reality bars often have holes. Now going into the stress razors in reality often have holes. We are talking about the bars. If there is any rectangular bar or circular bar, if there is any bar, so it often has some holes. There might be some holes in it, there might be some grooves in it. In case of shaft, you have seen that there are keyways, so that in that keyway you can insert the key. To insert the key, there are keyways in the shaft. Similarly, if sometimes there are grooves in the bar. Also there are sometimes notches also. Sometimes there is some V notches which are there in the particular bar. Also there are some shoulders. Sometimes it happens, as you can see in the diagram, this diagram is showing you that we can't ignore such type of change in cross section, because these change in cross sections are very important. So we can't remove these cross sections, we will have to keep. And these cross section, these shoulders create the stress, create very large stress in this area near to this shoulder. So in reality, bars often have holes, grooves, notches, keyways, shoulders, threads, or other abrupt changes in geometry that create a disruption in the uniform stress pattern. These particular, all these things, oil holes or grooves or notches, these all create a disruption in the uniform stress pattern, and these discontinuities are known as stress razors. These continuities are known as stress razors. As you can see, these are the analysis image of a particular rod or shaft having a shoulder. So these are the images, these are the results which are obtained through the ANSYS software, and you can see this is showing that the stress is higher at this particular portion. At this particular portion, this green particular portion is showing you high stress. Here similarly in this diagram also you can see this is the red portion. Red portion shows the maximum value of stress. Blue portion shows you the minimum value of stress. This red color portion shows you the maximum value. So this maximum value of stress, as you can see in this diagram also, it is here where there is shoulder. So we have to, our main purpose is to minimize this red zone, red zone minimize means this is the area where there is high stress. And if there is high stress, what will happen? Whenever the load will be applied, the failure will occur at this particular portion. The failure will occur at this particular portion where the cross sectional area has been reduced. All right, so as you can see here, there are other diagrams also. You can get an idea of the stress concentration or the stress razors. See, first diagram, here you can see this is the reddish, somewhat reddish area. Why? Because there is a hole made in it. Therefore here there is lot of stress concentration. Here also you can see there is change in cross section. Cross section was usually like this, but here what happened? Here there is a hole. Therefore due to this hole, this area has become weaker. How you know that this area has become weaker? Because there is large stress. This is the red zone area. Red zone area means there is maximum stress at this particular area. There is maximum stress at this particular area. So this zone which is showing red in color, this zone is showing you that the stress concentration is high at this point. The stress concentration is high at this point. Similarly, here also in this diagram you can see the plate with a shoulder. In this particular portion, this is somewhat red in color, means it is not pure blue. This means that the stress concentration is very much higher at this area. It's very much higher at this area. So these are some of the results obtained through some analysis software in which we can study about the stress which is developed whenever some load is applied on the plate. So when load is applied, these are the results that are obtained in particular member of the bar. See here, one more diagram is there. A hole is there. This is a hole, and due to this hole, you can see stress is increased. Here a shoulder is there. Due to that, stress is increased. And if you want to see, just cut it here. You will see that these are the stress lines which are showing that the largest stress lines is near to this hole, means maximum stress is near to this hole. Similarly, here also you can see this whole shoulder portion. The increase in the stress can be seen by this particular diagram. See, the stress line is maximum near to this shoulder, and it has got minimized, it has got smaller as we move away from the shoulder. So the stresses near the point of application of concentrated loads can reach values much higher than the average value, of stresses in the member, The region of the bar where higher stresses develops as a result of these continuities is known as stress concentration. This region of the bar where higher stresses is developed is known as the stress concentration. Alright, moving into the next slide. Design considerations. The maximum stress, which is denoted by sigma max, occurs at the edges of the hole. This we have understood, and may be larger than the normal stress. This also we have understood, that maximum stress, this occurs at the edges of the hole, and it may be very much larger than the normal stress, which is calculated by this formula. What is this? This is load by area, means the normal formula which we use for calculating the stress. For design consideration, the result obtained depends on the following. In case of a circular hole in a bar, we consider the ratio R by D. Alright, in case of a circular hole, if there is some circular hole, so for considering its design, what we take, the value which is important while considering its design is the R by D ratio. R by D ratio means it is R denotes the radius of this hole, and D denotes the thickness of this plate. D denotes the thickness of this plate. So this particular ratio is important for the design considerations of a plate with a circular hole. Now coming into the second case, for fillet, the ratio which is important, like see here there is some fillet which has been made. Fillet, this is fillet. So in this fillet, if you round off any corner portion like this way, so we say that we have made some fillet. So if you fillet it, so in case of this fillet, the thing that is important, the ratio that is important is R by D, where R is what? R is the radius of this fillet, and D is small d is what? Small d is the this minimum thickness of the plate, and capital D by D is what? It is the ratio of the larger thickness to the smaller thickness of the plate. If it is a circular cross section, then capital D will be the larger diameter and small d will be the smaller diameter. Alright, so these ratios are important whenever we consider the design of a plate having the fillet, either the fillet or the hole in it. Stress concentration factor. Now in order to estimate the value of particular stress concentration, we have used a factor which is known as stress concentration factor. The factor which estimates or which gives the value or picture of how much stress is concentrated at particular portion, then we use the factor stress concentration factor. Now what is stress concentration factor? It is defined as the localization of high stresses due to the irregularities present in the component and abrupt changes in cross section. Stress concentration is basically what? It is the localization of high stresses due to the irregularities present in the component and abrupt changes in the cross section. So in order to consider the effect of stress concentration and find out localized stresses, a factor called stress concentration factor is used. It is denoted by KT. It is denoted by this KT. T here, T stands for theoretical. T stands for theoretical stress concentration factor. Basically it is what? It is theoretical stress concentration factor. Normally we don't use the word theoretical always. It is generally used similar in the same way. SCF, stress concentration factor. What is it? It is the localization of high stresses due to the irregularities present in the component and abrupt changes in its cross section. Now there is a formula for getting the value of stress concentration. How you can get the value of stress concentration? It is a ratio, as you have seen, it is a ratio of highest value of stress near the discontinuity divided by the normal value of stress obtained by the elementary equations for minimum cross section. Means if there is a plate which has got the hole, then the stress which you are getting at this particular portion, means where there is normal stress, this particular stress, and the stress which is maximum which you will get here, this is the maximum stress. So maximum stress which you will get near to this hole divided by the normal stress which you will get at any other portion, normal stress is known as the stress concentration factor. Means sigma max means maximum stress near which is available near the discontinuity divided by the normal stress or the nominal stress which is obtained by the elementary equations for minimum cross sections. This gives you the value of stress concentration factor. All right, it is very important. You should know the formula. This AT is equal to sigma max upon sigma naught in case of normal stresses, and in case of shear stresses, it is equal to tau max upon tau naught. So this formula is important and it will be used in the numericals which we will solve later on. KT is equal to sigma max upon sigma naught, and it is also equal to tau max upon tau naught. Again, as design engineers, we are more interested in the maximum value of stress in a given section than in the actual distribution of stress in the section, since our main concern is to determine whether the allowable stress will be exceeded under a given loading and not where this value will be exceeded. For this reason, we define the ratio K is equal to sigma naught upon sigma average, where K is stress concentration factor. Now, analysis of stress concentration. To calculate the maximum value, first do the following. In order to calculate the maximum value of stress, we will have to do the following step. First, we will be calculating the average stress value in a critical region. And how we can calculate the average stress value? This will be calculated by the formula load by area, as we have been using as the elementary equation. And then what we will do, we will multiply the result by the stress concentration factor. As you know, the formula is also saying you that maximum by nominal stress will give you what? It will give you stress concentration factor. Implies that if someone needs maximum stress, then in that case first he will have to calculate the nominal stress by the elementary equation formula and then multiply with stress concentration factor. All right, so this is the process. Now note, this procedure is valid only as long as sigma max does not exceed the proportional limit of the material. Since the value of clay plotted in the graph below were obtained by assuming a linear relationship between stress and strain. How do we obtain the value of K? We make the use of graphs. There are some graphs which are used to find the value of K, and that I will tell you later on. Now coming into what are the various causes of stress concentration. Let us list out the various causes of stress concentration. The first reason of stress concentration is the variation in the property of material. Variation in the property of materials. There are variations in the property of material that we will discuss. First of all, first cause is this. Second is the load application. Third is the abrupt change in section. Fourth is the discontinuities in the component, and the fifth is machining scratches. So these are the reasons for the stress concentration. First, there might be some property variation in the properties of material. Second, the type of load may be different. It either may be some other load. So based on the load application also, the stress concentration is different. Then the third is if there is any abrupt change. This we have already discussed by taking the example of a hole drilled on a plate, or the shoulder made on any plate. And then if there is any discontinuity in the component, and if there are scratches also in the surface of a machine member, then also that it also increases the stress concentration. Now one by one we will go into the each cause and elaborate that particular cause. First, the variation in properties of material. In design of machine component, it is assumed that the material is homogeneous throughout the component, but it doesn't happen like this. So there are materials which are not homogeneous completely. In practice, there is variation in material properties from one end to another due to many reasons, due to many factors. And what are the reasons, what are the factors for this variation in mechanical properties? There are many factors. Like first, there might be internal cracks and flaws like blowholes. There might be internal cracks or flaws like blowholes. There can be cavities. If there has been welding done to make the product, then there can be some air cavity in that welding. Then there also can be some air holes in the steel component. While manufacturing the steel, there might be some air holes which have been left. Then there might be some non-metallic or foreign element in that particular product. So that also creates a variation in the property of materials. These variations act as discontinuities in the component and cause stress concentration. Second important factor for increasing stress concentration is the load applications. Machine components are subjected to forces. These forces act either at a point or over a small area on the component. Since the area is small, the pressure at these points is excessive. This results in stress concentrations. The example of these load applications are as follows. See, one of the reason is the load application also. If there is some point load, this type of load, if it is acting at some point of a bar, this will increase the stress at this particular area. If not in this way, if this load is applied at whole of the area uniformly, then the chances of failure are less. Why? Because the stress is not getting concentrated at any point. So this is the thing that is being told, that if the area is small, the pressure at the area where it is where the load is acting, it will be excessive. So what are those particular cases? You can see this particular problem in the gear trains, where there is meshing, where there is contact between the meshing teeth of the driver and the driven gear, where there is contact between the driver and the driven gear. As you can see, the teeth of one gear presses into the teeth of the other gear to move it along with it. So for that, this particular load acts again and again, and this is on a small area, and therefore this increases the stress concentration at this area. Then after, there is the case of cam and follower. In cam and follower also, what you see, there is a follower and there is a cam. And the joint between them, the load of contact between them is also very less. Then comes the case of ball and the races of bearing. In case of bearing also, if you will see in bearing, there are balls and the race of the bearing, they have very less contact between themselves. So this creates localization of stress in this particular small contact area. Then the fourth is the contact between the crane hook and the chain. In this case also, there is this problem. So in all these cases, the concentrated load is applied over a very small area, resulting in stress concentration. Coming into the next factor. The other factors for increase of stress concentration is abrupt change in section. So this we have discussed, like in case of pulleys, ball bearings, sprockets, gears. If you have to mount these all rotating element to the shaft, if you want to mount these element to the shaft, then what you will have to do, you will have to make some shoulder, you will have to make some straps on the shaft, which are also known as shoulders. So like this, if you have a shaft, so in order to mount some pulley, some gear, some sprocket or some ball bearing on it, what you will have to do, you will have to make some step on it, which is known as shoulder. So in this way you fix the pulley on it. So for that you need shoulder, and this making of this shoulder increases the stress concentration. So this is basically what, this is abrupt change in cross section. The cross section was this much and suddenly it became small like this. Although these features are essential, these features are very essential, these can't be ignored, but they create change of cross section of shaft. This results in stress concentration at these particular portion. The next factor is the discontinuity in component. The next factor is the discontinuity in the component. Certain features of machine components such as oil holes or oil grooves, keyways and splines and screw threads results in discontinuity in the cross section of component. Alright, there might be some oil hole, like in case of bearings, there are large bearings in which you have it is needed to have some oil holes also, so that you can pour oil through that particular groove or holes. Similarly, for fixing any rotating element to the shaft, you have to make keyway on it. Similarly, sometimes there are splines cut on the shaft. All right, there might be some threads, also. You all know there can be some threads in a rod. So these threads also increase the stress concentration. All right, so these are the discontinuities in the component. Then there might be some scratches on the surface, like inspection mark or stamp mark. So these scratches also, if this is the surface and there are scratches on it, so these scratches also act as stress raisers and increase the stress concentration. So these were all the factors which results in increase of stress concentration. So how, now the question is how we can remove or decrease this stress concentration. So first important line which has to be kept in mind is that although it is not possible to completely eliminate the effect of stress concentration, but there are methods to reduce stress concentration. So keep it in mind, completely reducing the stress concentration is not at all possible, but we can reduce the stress concentration. Completely eliminating the effect of stress concentration is not possible. You can reduce the stress. All right, and this is achieved by providing a specific geometrical shape to the component. How this is achieved? This is achieved by providing a specific geometrical shape to the component. In order to know, first of all, to what happens at the abrupt change of cross section or at the discontinuity and reduce the stress concentration, you can see the figure. In this figure, we have made a flow analogy. We have made a flow analogy between the flow phenomena and this stress phenomena. Through that we can understand that what is the problem. Like we all know, there is a similarity between velocity distribution in a fluid flow in a channel and the stress distribution in an axially loaded plate. The equation of flow potential in fluid mechanics and stress potential in solid mechanics are basically more or less same. The equations involved in fluid mechanics and stress potentials are more or less same. Therefore, it is perfectly logical to use fluid analogy to understand the phenomena of stress concentration. So, when the cross section of a channel has uniform dimensions throughout, the velocities are uniform and the streamlines are equally spaced. The flow at any cross section within the channel, we all know, is given by some equation. Q is equal to UDA. I have not added that particular equation, but it is not relevant here. But we also know that the stress equation is P is equal to sigma into a small area dA. So you can see they are more or less similar to each other. Now when the cross section of the channel is suddenly reduced, when you reduce the cross section of the channel, the velocity increases in order to maintain the same flow, and streamlines become narrower and narrower and they crowd together. A similar phenomena is observed in a stress plate. In order to transmit the same force, the stress lines come closer and closer as the cross section is reduced. As you can see here also, that in this diagram, the stress line have come closer and closer. The stress lines have come closer and closer as the cross section is reduced. Alright, at the change of the cross section, the streamlines as well as the stress lines has to bend. When there is sudden change in cross section, bending of stress lines is very sharp and severe, resulting in a stress concentration. These stress lines have to bend sharply, and due to this sharp bending, there is stress concentration. Therefore, stress concentration can be greatly reduced by reducing the bending by rounding the corners. All right. One more, the streamlined shapes are used in channel to reduce the turbulence and resistance to flow. Streamlining or rounding the counters of mechanical components have similar beneficial effect in reducing stress concentration as we do in case of flow phenomena. Here in the stress concentration also the same can be used because there is some analogy between the equations. The equations are more or less look similar. The equations which are used in fluid phenomena and the equations which are used here in stress considerations, the equations are so same. Therefore, since we do streamlining in case of flow phenomena, here in fluid also, in here in stress also, we can do the same thing. We can we can smoothen the cross section. We can round the corners of the particular element where there is increase in stress concentration. All right. So coming into the next one, first important measure which we can take is the use of additional notches and hole in tension member. Use of additional notches and hole in the tension member. Now a flat plate, I will show you a diagram. The severity of stress concentration can be removed by three methods. If there are notches and holes which have to be made, so in order to reduce the severity of stress concentration, these three steps can be taken. First, use of multiple notches. Second, drilling additional holes. Third is the removal of the undesired materials. This method of removing the undesirable material is known as the principle of minimization of material. Principle of minimization of the material. This particular method of removing undesired material is known as principle of minimization of material. Now, how it happens? I am showing you. See, in this diagram, you can see a flat plate with a V notch is subjected to tensile force. It is observed that a single notch results in a high degree of stress concentration. The severity of stress concentration it can be removed by first use of multiple notches, as you can see here. In place of a single notch, make some multiple notches in the vicinity of that notch. All right. Then the second is drilling additional holes. Second is you can drill some additional holes near to this notch portion. And the third is removal of undesired materials from the vicinity of that particular notch, which has to be made due to some functional requirements. So in these three methods, the sharp bending of a force flow line is reduced and it follows a smooth curve. It follows a smooth curve. All right. Now, second step is what? Second step is fillet radius undercutting and notch for members in bending. Second, if you have some members where is some bending load acting, if you have some shaft which has got shoulder in it, and if there is some bending involved in it, so what we will do in that case, let's see. In case of such cases where there is shoulder and some bending load is acting on it, due to which there can be some failure. So in such cases, what we do, the shoulder creates a change in cross section of the shaft, which results in stress concentration. As you can see in the diagram, a bar of circular cross section with a shoulder and subjected to bending moment is shown. Ball bearings, gears or pulleys are seated against these shoulders. There are three methods to reduce stress concentration at the base of these shoulders. So these three methods are shown in the diagram also. As you can see in the first method, this is the first method which can be used. In this method, what we have done, we have used a fillet in place of this pointed portion. What we have done, we have smoothened this particular portion so that we have given a particular fillet radius to it. This results in gradual transition. As you can see this stress line, this results in gradual transition from a small diameter to large diameter. The fillet radius should be as large as possible. This fillet radius should be as large as possible to reduce stress concentration. In practice, the fillet radius is limited by the design of mating component. It is but generally what happens, you can't increase too much this fillet radius due to limitation in the mating parts of the design component. All right, now coming into the second step, in what we can do in the second step, we can do undercutting. We can do undercutting. How we can do undercutting? As you can see in the diagram, this is the undercutting. Due to this undercutting also, stress lines are not abruptly changing its location. All right, and in the next one of the other step, this is the first step where we have made fillet radius, we have done fillet, and in this we have done undercutting, and in this we have done notch. The effect in all these three is same, that stress concentration has been decreased in this portion. Why? Because these stress lines are smoothened, they do not change abruptly. So coming into the next, what we can do, if there is a case, now coming into the transmission shaft with a keyway, if there is any transmission shaft with a keyway, and in that case what happens, this keyway, this particular keyway, this keyway increase, this keyway is a discontinuity and results in stress concentration at the corners of the keyway and reduces the torsional shear strength of the shaft. It reduces the torsional shear strength of the shaft. So therefore what we can do in this way, in this case what we can do, we can drill some additional holes for the shaft. What we can do, we can drill some additional holes. We can drill some additional holes near to that keyway, and these two holes should be symmetrical to each other. These two holes should be symmetrical to each other. If you are drilling a hole here, then just symmetrically on the other side of this particular keyway you will drill and the other holes. Due to this, what will happen, these stress lines which were abruptly changing when there were no hole, these stress lines do not change abruptly, they are smoothened. All right, so this is also one of the important method. Now coming into, now let's discuss some quizzes, multiple choice questions to assess the understanding of the whole of the lecture of today. See, first MCQ number 1, making a hole in a plate dash stress concentration. So we all know, if you make a hole in a plate, what will happen, stress concentration will increase. So A is the correct answer. Second, making keyway in shaft dash stress concentration. Again the same thing, if you make a keyway in the shaft, just now I have told you, if in a shaft you make a keyway, what will happen, this will increase the stress concentration. So A is the correct answer. Coming into the MCQ number 3, making of additional notches in a V-notched plate. Now if this is the V-notched plate, and if you make additional notch to its vicinity, what happens, this is basically done to reduce the stress concentration, because they smoothen the stress line, so it reduces the stress concentration. B is the correct answer. Then streamlining or rounding of the corners. What be the reason why we round off the corner? If the corner is like this, why we give it a round shape? So in order to get a smooth streamline, smooth stress line, and therefore what is the purpose? It reduces the stress concentration. So B is the increases stress concentration or decreases stress concentration. Shoulder in shaft, it is very easy. If you have a shoulder in shaft, if you have a shoulder in shaft, it will increase the stress concentration. If this is the shaft and it has got this shoulder, there is abrupt change in stress lines. Therefore, it increases the stress concentration. Then MCQ number, again coming into the MCQ number 6. A streamline or rounding of corners, again it will reduce the stress concentration. Whenever you round off the corner, it reduces the stress concentration. MCQ number 7, what is the stress concentration factor? So by the definition which I have told to you, it is the ratio of the maximum stress divided by the nominal stress. So first option itself gives you the correct answer. It is the ratio of maximum stress to the nominal stress. So option A is the correct option. Coming into the MCQ number 8, the localization of high stresses due to the irregularities present in the component and abrupt changes of the cross section are called as, this is a stress concentration. By definition we have seen that what is it? It is the stress concentration. Then after MCQ number 9, variation in properties of material. Variation in properties of material is caused, why it is caused? It is caused due to internal cracks, yeah. Cavities, yeah. Air holes, yeah. If all these three are correct, means this option D is the correct option. Then machining scratches, what they do? They increase stress concentration. So A is the correct answer. So all the multiple choice questions have been discussed with you. You just go through all these MCQs and the video lecture. And if you want some more stuff or some more study material regarding this particular content of today, then you can use these references. These are the references which you can refer for your studying. In this, the content which is mainly used by me in this particular subject are from the design of machine elements from V.V. Bhandari. Apart from that, the mechanical engineering design book by Shingle, that has also been used. So I hope you have understood the today's lecture. In the coming lecture, we will discuss more into the machine design subject. Thank you and have a nice day.